So hope my screen is visible to all. Just give a small reply in the chat. Everyone, my screen is visible to all. Fine, thank you very much. Okay, today we are going to learn the next phase of our VLSI. So actually, this is actually system Verilog. So why, first of all, before why we are actually learning system Verilog? That's a big question, right? So till now in Verilog, you are able to design so many designs. So you are able to code so many designs. You are able to understand designs, and you are verifying all the designs using the test bench. What you do, like linear test bench or self-checking test bench like that. And now, why we have to learn system Verilog? In general, system Verilog actually a verification language. So it comes both. It is able to we can design any RTL code and we are able to verify the RTL code. In general, we'll do that. But why system Verilog? You know, the complexity of the design increasing day by day. So that's why we have to learn the test bench which should verify the complex designs also. So that test bench actually provided by the system Verilog constructs. So we have learned, now we are going to learn so many data types and so many inbuilt constructs which supports to verify the complex RTL designs. There's nothing but system Verilog. So in this class, we are going to learn what are the data types, arrays, interface, the coding examples related to this. See, in this session, we are going to learn what is actually system Verilog, why we are actually moving from Verilog to system Verilog, and complete system Verilog data types, arrays in the system Verilog with an example, and interface and the concepts in the interface like baud ports, clocking blocks like that, and RTL plus verification coding examples and interview and some exercises related to that. So what is actually system Verilog? System Verilog is an extension of Verilog HTL. So actually Verilog has some, let's take 30% of 25% you learn in this Verilog. So the extension of the Verilog, so it actually an advanced improvement of the Verilog. It supports both RTL design and verification. So design, not only designing, so we have to verify the corner cases of the design also. Then only the design is like perfectly fabricated without any bugs. So we have to verify all the test cases, and that too complex design we have to verify. That's why we are going for system Verilog and provides advanced data types and OOPS concepts. So in Java, many of learn about OOPS concepts. So OOPS concepts actually supports in system Verilog. System Verilog actually the combinations of different languages. So actually there are so many languages what we learn. So there are some concepts from all the languages can be taken and the system Verilog actually improved. So from the Java, OOPS concepts is introduced in the system Verilog for improving the used widely in ASIC and FPGA industries. So both ASIC and FPGAs uses this system Verilog for verifying the complex designs. Why move from system Verilog to Verilog? Because I like why we have to move. As I said before, Verilog lock strong data typing. So it actually whatever the data types you declared in the Verilog, all are the memory is allocated in the compilation time only. So like right, compilation, compilation time and simulation time. There are two actually. This is compilation time, and another one is simulation time. So there are two actually. The compilation time itself, the memory is allocated in the Verilog. So almost every construct in the Verilog or allocated the memory in the compilation time itself. But in the system Verilog, so after the compilation, the step where I just the simulation time. So at this time, the memory is allocated. So the memory is going to be saved a lot. That's why system Verilog actually supports this type of memory allocation. And complex verification environment were difficult. See, in Verilog, we can't create a complex verification environment. Like in future, we are going to learn about drivers, motors, and generators, drivers like that. So that environment is not supports in Verilog, but system Verilog supports that one. And large module like connections. So as I said before, this actually complex designs. So complex designs actually what happens? While verifying complex designs, we have thousands of signals. So the connections becomes verbose. So pin-to-pin connection we have to give. So we have to introduce another concept like interface in the system Verilog. It supports in system Verilog. So through this, the connection between modules and modules can be easily taken place. And that is only I am saying about interfaces. And see, for verification, advanced bug verification, we have assertions and randomization topic is there, and coverage driven verification is there in the system Verilog. But these don't support in Verilog. That's why we are going from Verilog to system Verilog. See, in Verilog, there are certain limitations out there. So what are the limitations here? The limitations, so limited data types. So there are only two data types, wire and rich data types, and no inbuilt support for advanced arrays. So it won't support advanced arrays. If the arrays comes means actually we can verify the memory related things easily. So no object oriented verification in Verilog and difficult test bench architecture. So, as I said before, there are actually till in Verilog we have a linear test bench only, but in system Verilog we have architecture verification. So we will build the each component for specific functionalities, and we will integrate all the components in our test bench, and we will provide the functionality of the component separately, and we will integrate them, and we start working with them. Like the communication, we will generate the communication between each component. Then all the components will integrate it to verify an RTL. Like that we are going to do. So hard to scale up complex SOC verifications. Verilog won't support for SOC verification. Verilog only supports up to IP verification. IP. So Verilog only for IP verification. But system Verilog also supports SOC verification. See, these are the advantages of system Verilog. Rich and stored strong data types. As I said before, we have so we will introduce the we'll discuss further. Powerful array structure. So arrays are the very good concepts to verify any type of design. And interfaces, simplified connections. So in the Verilog we have the connections, the complex connections are there. Here the connections becomes very simple that we come to know. And assertions help to detect bugs easily. Not only verifying design, but we have to find the bugs faster. So as a verification engineer, we have to find the bugs faster in our RTL code. So that assertion concept as introduced in the system Verilog and used for as a foundation of UVM methodology. UVM is the next step as it's actually a further step for it actually contains system Verilog language only, but it's actually this is a for like advanced step to verify ultra like more than complex designs like CPU verifications and overall motherboard verifications are there, right? So that at that time we use UVM methodologies. See, as I said before, this is just an intro. This actually the components. So right, test bench. So till now in your test bench, mostly what you did. So you just generate a clock and you start declaring the signals, and you just assign the values in the to the signals. Automatically the values is assigned to you are instantiating your design. That's it you are doing till in Verilog. But in this test benches, in your system Verilog test benches, we are going to develop so many components using class-based verification. So actually it's a class-based verification. So we are using. So these are all the components we are going to code first. Generator, driver, DUT, monitor, scoreboard. Through these components, we are going to verify an RTL code or a complex RTL very easily. And is actually the main concept I want to say. The reusability is more in system Verilog. Whenever you test, when like you return a test bench, that test bench should be used to verify other designs also. That actually possible in system Verilog by writing the code which is reusable. So the reusable code you can implement using system Verilog. So this is the verification. So coming to the data types, system Verilog actually have many new data types like two-state data types, four-state data types. In Verilog, most of you know only four-state data types, but in the system Verilog, two-state data types are introduced to save the memory. Simulation time is actually reduced. So integer-based types are also available, and packed and unpacked arrays. So actually, let's take that will be introduced further. Packed means like every bit is packed. Unpacked means we can what you call assign the values differently and we can manipulate them. These types of improvements modeling accuracy. So for improving the accuracy, we are introducing these type data types. So these are the two-state data types. Only two-state means it won't store X and high impedance. It only stores 0 and 1. and actually it's a bit. So bit is a type of one data type. It actually stores a single value, so 1 or 0, that's it. Byte actually what? It stores 8 bits, so it will look like this. So it's actually a packet type, so the memory will be allocated like this. Whenever you declare byte A like this means, so it actually contains 0 to 7 bits, so 7 bits, and they are signed or unsigned, you have to know. So just have an assignment like that. So which is signed and which is unsigned, you have to make a note of, like in your own notes, make the note. So these are actually the data types. This is actually short int. This is also 16 bits. Like it will store from 0 to, that actually numbering system is from 0 to 15, is able to store 16 bits. And int, it is actually, int is actually 32 bits. So just know the difference between int and integer. Note down this question. What is the actual difference between int and integer? Okay. And long int. The long int means it stores 64 bit. So your assignment is like you have to know which are all signed or unsigned and what are the default values of each data type. That you have to note in your own notes. And see, this is actually two-state data types. This is a small example to understand. See, are you declared here? We are using bit flag, byte data, int, counter. These are all your wish. These names can be your wish. And the compilation, like it's in the simulation time, what we are assigning for the flag, it's actually what I said, actually a 1 bit data type. 1 bit means it can store able to store 1 or 0. So here we are assigning 1. If we assign 11, it converts to, if you are assigning binary value 11 means it will truncate. So it will truncate the MSB values and it will store only the LSB value, and that is 1. So whatever the value you give to the flag, it will truncate all the remaining bits and it's take only 1 bit, like that. Data. So data here, what data is actually a byte and it's actually storing 8 bits of data. So here they are assigning 8 tick hexa. Hexa means like 4 bits, like 4. 4 bit A. A means what's the hexa value of A? You know, right? So that for like in total 8 bits are allocated. So that's the thing. And a counter. Counter int means 32 bits value and it's storing 10. So it can able to store 2 power 32. 2 power 32 is the maximum value of int, right? So it can store, the maximum value is 2 power 32. So just we are storing 10. It can able to store. No truncation happens. This is a small understanding of two-state data types. See, four-state data types are available. So supports. So four-state data types means these and all extra two values will be have. Logic is most common basic type. So logic is a four-state data types. Till now we studied about two-state data types, but logic is a four-state data types. And while is used for continuous assignment. So while is also there, since I will know we discussed before, system Verilog is an extension of Verilog. So what and all things in Verilog, that everything will be there in the system Verilog. In addition, we have some other features. That's the thing. Reg. So reg is the legacy type for Verilog. Right? Reg also will be there. Wire also will be there. Logic is there. So what's the importance of logic? Okay, it will replace both reg and wire. So right, in test bench, if you just recap, in test bench you are declaring inputs as reg and outputs as wire, right? Before, like instead of declaring wire and reg, we can just declare that as logic. So that confusion now we are going to avoid using logic data type. Just we can use logic data type. So logic data type supports both for like always block it will support, as well as initial begin it will support, like anything. Continuous assignment as well as procedural assignment, logic data type will be supports. So this is the last thing. See, we declared the module name and some input. So instead of reg or wire, we are declaring it as logic. So it can be used both in the procedural block as well as continuous assignment block. See, now we are directly using in the always block. So always FF. So why this is FF again? So always blocks are actually so many types in their system Verilog. So always FF is there. Like especially if you are developing a sequential logic, we have to use underscore FF. If you are using like combination logics, we are actually want to improve. So we have to use always underscore comb. Like that, separately we are using always blocks also two types here. And why we are using always differently? Why means, so if you are implementing any combination logic in always flip flop, it will automatically throw the error. So that for automatic bug detection, we are using always FF. So if you use blocking assignments here, automatically it will throw the error. So for easy bug detection, the developers developed like this. So just know the difference between always FF and always COM and signed and unsigned. So actually here only signed numbers represent only positive values. Unsigned. So unsigned actually you only have positive values. Signed, plus and minus we have negative values also can be stored in our data types and key. So if you almost everything, so let's take any data type is unsigned by default. So if you want to make it as signed, just you have to use the keyword called signed before that one. Okay. Common use of arithmetic operation. So signed if we actually performing any arithmetic operation, we need a signed variable. That's why we have to externally declare the signed keyword before our data type. So we will see an example of that. See, so by default logic is unsigned. But if you want to make our logic data type as signed, so we will declare like this logic signed 7.0 B. So now logic, so B is able to store 8 bits of data, okay, or 1 byte of data, which is actually signed. So the last MSB bit, so if I take this one, so this is a 0 and this is the 7th last bit. So this 7th bit can be allocated especially for a negative value. If 0 we have means it's a positive and 1 we have, it is actually a negative. Like that we can store both negative and positive values. So that actually externally we are making use of signed keyword to make our variable as signed. See, packed arrays. Now we are going to learn about what is actually array. So array is a set of values. It can store multiple bits of data. So it can store multiple types of data also. It can be able to store strings. It can able to store values. It can able to store characters. Everything you want. So here what we are doing, packed arrays. So packed arrays are nothing but declaration looks like this. First of all, just note the declaration. So you can use any data type you want, like what you call logic you can use, bit you can use, and you should not use byte. Byte before itself it says 8-bit value. So before you should not use byte here, and int long int that too you should not use here. Only 1 bit of data, 1 bit of so which actually store 1 bits, that data type we should use. So it actually vector type, right? So here we can use logic, we can use bit data type, and we can use wire range also. After that we are using 7 down to 0. So now data is a variable which is able to store 8 bits of data, but it is actually a packet. So packet, if you use left side means then it can be called as packet. But if you use right side means anything right side after the variable, that can be called as unpacked. So most RTL signals are packed only. Everything, whatever the design you are implementing in Verilog, if you remember, all are almost packed data types only. So we can actually, what do you call, let's take, so this is actually the structure, 0 to 7. So bit, so each bit you can manipulate. So if you want to store something value here, you can store. In the packet data types, bit manipulation will be there. So you can assign the value or you can remove the value also. But in the unpacked, whole thing can be replaced once a time. That's the difference between packed and unpacked. So here bit level manipulation will be there in the packed, but bit level manipulation is not there in the unpacked. So this is a simple example of packed array. So all the 8 bits are assigning the default value, some value we are assigning. So we can use decimal also. We can use binary, hexa, anything you can use here. So just if you want to use hexa means stick h you have to use. If you want a binary decimal means stick binary decimal you have to use like this. So, but before the thing, how many bits of value you have to store? 8, right? So that much value you have to see. You should be aware of here. How many bits you declare, that should be here actually. If you use some other means, automatically the slicing happens. So truncation happens. So loss of data will happen. So you just be aware of this. Unpacked. As I said before, unpacked declaration looks like this. So directly you can give 8, or you can give 0 down to 7, or 7 down to 0, anything your wish. The right side part. So first of all, data type we have to specify, and the variable name, and then the size of the unpacked array. So now it is able to, now actually the structure looks like this. Just for our understanding, we have to do like this. So actually there are 8 locations. So 0 to 7 locations will be there here. So each location, how much data, what's the data, maximum data it can store? Logic, just logic. So logic means like what? In each location it can store 0 or 1, that's it. So in each location 0 and 1, that's it. So what if you use logic 7 down to 0, data 8? So if you use logic 7 down to 0, data 8, if you use means, so each location we can have 0 to 7 again. So what's the maximum value we can store in each location? 2 to the power of 7 to the power of 8 is the maximum value, minus 1 is the maximum value we can store in this location. Okay, like that. If the declaration changes means automatically the structure will change. This is the actual unpacked array. So here no bit level manipulation, we can't do bit level manipulation, whole thing we can assign at a time. So there are actually 8 locations. Each location we can assign a random value like that, but bit by bit we can't assign the value. We can assign directly. So how to assign a value, you should know it. This is actually a declaration. Oh, okay, we declared what, how to assign the value, you should know. So logic data 8 you did. How to assign the value, we'll see. So we declared actually a unpacked type. So how to assign a value, we have to specify data of 0. So means like what? So we are actually trying to access the 0th location, and at the 0th location we are going to store the value of 1. Only we can able to store only 1 and 0, not any other big value. Why means we are using only logic here. If we use here something like, if we use here like 7 down to 0, as I said before, logic 7 down to 0, data 8 if you use means, in each location we can able to store 2 to the power of 8 minus 1. That's the maximum value we can store. 0 to 2 to the power of 8 minus 1 is the maximum value we can store here. That's the thing. So like that, based on declaration, the memory storage will actually changes. See, packed array bit level. So as I said before, this is a packed type array. So here actually bit by bit we can access and we can manipulate. Okay. So this is the 0th bit and this is the 7th bit. So multi-dimensional arrays also there. So this is actually a single dimension arrays we learned till now. So there are multiple dimension arrays of structures, useful to model memory blocks. So if you are working on big memories to verify RAM, ROM like that, we can use multi-dimensional arrays, common in memory design. So if you are working on memory designs, if you are trying to verify memory designs, we have to learn about what are the multiple dimension arrays. So it's actually 2D array. As I said before, multiple dimension array is nothing but more like 1D. After 1D we have 2D, right? From 2D onwards we can call them as multiple dimension arrays. So this is actually a multi-dimension array. So as I said before, one second. Yeah. See, before example only. So we can assign the values like this. So multi-dimension is an example of multi-dimension array. We can assign the values like this. So what's the maximum value we can assign? We can assign 8 bits in each memory location. We can assign 8 bits. So dynamic array. So just right now, up to now we learned about just actually simple fixed arrays. Now we are going to learn about the dynamic arrays. Fixed arrays actually, if you go before 2D array, multi-dimension array, package and all, the memory will be allocated at the compilation time only. But that will consume more time. What if you want to allocate the memory in the runtime or simulation time? If you want to allocate the memory in the simulation time, we want to go for dynamic arrays. So if you go through here, the memory size is fixed here. So we can't able to change the memory. But now we can able to change the memory in the runtime. So let's take, we have 10 locations. We can change 10 locations to 20 locations in the simulation time. the flexibility will comes now. This is actually comes through dynamic array. See, array size determined during runtime. So in the runtime itself we can assign. In runtime only we can assign the size of an array, not in the compilation time. So how we can allocate the memory? We can use the new construct, new square brackets we have to use. Used frequently in verification environment. So in the verification environment, as I said before, dynamic arrays are especially used for verification related. In system verilog itself for verification only. Most verification constructs are there. So memory can be resized dynamically. Resize means nothing but we can change the memory. In the runtime itself, let's take 20 memory we have right now. We can change to 30 in the runtime. That flexibility will comes. How we can change? See the exact example. See, this is the declaration of dynamic array. So it's actually data type. We can use any data type and name of an array, and we are using square brackets. So we are not saying anything in the compilation time. This is actually compilation time. So it is also everything will be compiled. Okay, it will compilation time with nothing but we can any bug is there, any proper syntax error is there, it can be found. But the main values assigned at the simulation time. The simulation time. Coming to simulation time, it will go inside the initial begin block. So initial begin block actually can have delays also. See, in the dynamic array, we are first of all we have to allocate the memory. Just we have declared the array, but we not said what's the size of an array. So this is the size of an array. So if you use like this, 10 memory will be like 10 locations will be created. So each memory, so here 0th location and it's the 9th location. So in each location it is able to store int data type. So what's the maximum value it can store? 2 to the power of 32 minus 1 is the maximum value it can store in each location. So like the 10 locations are there. How to assign the value? We discussed before in fixed arrays like the same, like that one. But it can be in our control. Now we have 10. So what if you want to make it as 20? Again I will call this name here. Before end here, I can use the name here, dynamic array, and equal to new of 20. Now separate 20 location will be allocated again. Like that we can increase the size of the memory, or you can change the size of an array in the simulation time. It's in our control. But here it's not in our control. Once the array is declared, we can't change the size. So associative arrays. There are actually so many arrays, but we are going to again associative arrays. So we actually memory saving concept. Dynamic arrays itself saves some memory. Let's take in fixed arrays. In fixed arrays, once the memory is allocated, let's take 8, like in the compilation time itself, memory is allocated in fixed arrays, as I said before. We assigned 8. Okay. So what if we not use all the locations? The memory will be wasted. In the dynamic arrays. Dynamic arrays, some flexibility now came. So what's the flexibility we got? We can allocate the memory in the simulation time, not in the compilation time. So it's actually some memory saving happens. What if we use associative arrays? So associative arrays helps us whenever we store the value only, the memory is allocated. Without storing any value in that array, memory can't be allocated. That actually associative array brings that feature. See, index type can be any type. So we can use index string. Index can be any type. Efficient upper space memories, sparse memories. Memory allocated only when it is needed. So in the dynamic arrays and the fixed arrays, whenever we declare the memory, automatically memory will be allocated in the computer or in the memory storage in our hard disk. Even though we use it or not, the memory is allocated. But in the associative arrays are different. Whenever we store something in the associative array only, the memory is allocated. So the memory storage, like it is actually consuming less memory. That's why it is very much useful in the verification environment. See, this is actually declaration of associative array. This is actually the data type which we want to store in that associative array, and this is the index. So it can be any type. It can be string data type. It can be bit data type. Here you can have bit also. You can have byte also. Anything. If you use bit, means only there are two locations, 0 and 1. If you use byte means we can have 8 locations, 0 to 8 locations we have. And in each location we can store int data type. So see, oh, how many string? So string means okay, confusion, little bit confusion. Here I am using byte. Let's take byte I am using here. Instead of string, I am using byte here inside. So byte means how many bits? 0 to totally 7. So totally 8 bits it can have. Okay. So each actually a name. It's actually a key of key. We can call it as key of associative array. So it can look like this: 0 to 7. If you use inside byte, and in each memory location it can store int data type. It can store what's the maximum it can store, 2 to the power of 32 minus 1 it can store. But just by declaration, so the memory will be allocated. Just by declaration the memory won't be allocated for, but whereas for fixed arrays, but whereas for dynamic arrays, but just by declaring in the runtime, the memory is allocated. This memory will be allocated for dynamic arrays and fixed arrays. But associative arrays memory is not allocated. Whenever we try to store a value only, here we are trying to store 100. For this only memory will be allocated. For this remaining place, there are some remaining places there, right? That remaining place memory is not allocated. So this actually saves a lot of memory. That's why we are learning associative arrays. Now queues. Queues are actually a FIFO type. So FIFO is nothing but we can send them and we can grab them. We can push and pop them like that. So dynamic FIFO style. The queues actually follow FIFO related operations. Push and pop, push friend, pop friend, push back, pop back, like that operation will be there in our queues. We can insert in them, and it is actually a flexible type. So actually it will increases. The size will be flexible. If you keep on adding the things, automatically the size will be increasing. So if you keep on popping the things or you can deleting the things, automatically the size will be shrinks. So that's the advantage of queues. Let me show the declaration of queues. This is the declaration of queue. So into data type, we have to specify the data type and then we have to use the dollar symbol here. Here is actually your wish, whatever the variable name, and inside you have to use this dollar. Then it will be actually turns a queue. Queue. How can you store the values in the queue? We can use the methods called pushback, pop friend, and there are so many methods. So for your thing, like guys, you have an assignment like explore all the remaining methods, what and all in the queues. There are so many methods in the associative arrays also. There are so many methods in the dynamic arrays also. Explore all the remaining methods and learn about them. So now we are going to learn about interfaces. As I said before, why we are learning interface means for the connection management. In the Verilog, if you want to connect the thousands of 2000 signals, it's become very difficult. But if we can use the interface concept, so let's take in the Verilog our design. Let's say there is a chip which have n number of signals. So each signal we want to connect to some other module. Is there? So like this we have to connect each pin like this. Pin to pin connection we have to do. But in the interface, all the signals first we declare. Let's take it's a pipe. Just imagine this one. All the signals, what are the signals we are there? We are just declaring inside the interface, and we are just connecting the both. This is one chip, this is another chip. Just we are connecting this interface to another chip just by declaring two lines of code. All the connections will be connected from this module to this module easily. So the number of lines of code is decreases, the time saves, and the confusion is avoided. That's why we are learning the interface concept. So interface actually a bundle of signals, reduces large module ports, improves code readability. Interfaces are heavily used in verification environment. Let's see how. And through interface you can learn, you can implement both RTL, we can implement an RTL design, and we can implement a test bench also. So there is basically a connection between RTL and test bench. Let's take simply. This is RTL and this is the TB we are implementing. Just a connection between RTL and test bench. And the thing is like interface is static type. So whenever it's declared, the memory is allocated. But our TB environment is now we are going to learn the TB environment. It is actually a dynamic type. Then we have to convert our interface to dynamic, and then we have to give the connection to the test bench. So like this connection will be avoided. So simply this is a test bench and this is RTL, and we are just, it's actually a mediator between test bench and EUT. So this is the interface we are going to learn slowly. See, this is actually declaration of interface. So interface name we have to give, and what are the signals in the RTL? You know, RTL, each and every signal should be declared as logic data type. Why logic only? As I said before, it can be used to avoid the confusion as what the signal may be reg or signal may be wire data type. To avoid the confusion between them, we are going to use logic data type. So every signal, what are the signals we have in our RTL design? Each and every signal can be declared here, and interface can be reused. Now this interface can be used to implement RTL as well as test bench. That you have to learn. So how can we implement an RTL code using interface? How can we implement a test bench using interface? That is your task. Just learn through internet. So just take a test bench of D flip-flop. So how to develop RTL code using D flip-flop using interface of D flip-flop. So how to develop test bench for D flip-flop using interface. That is your task. Just go through. So this is actually how we have to use the interface. You declared interface, okay. So this is the interface name we have to use. So this name is very important. This name can be used in our designs. See. So we are having the module in general module name. So see, bus interface and interface instance you are giving again. So bus interface can, if you call this name, automatically all the signals will be called in our RTL design. So automatically the port list now is replaced with all the three. Like how many signals we have? Totally three signals are there, right? That three signals will come inside if you use like this. Now, how to assign the values? So now in the interface we have clock, we have reset, what and all signals we have. Now in the interface we have clock, reset, and data. What if we want to assign any value for them? So we have to use the instance name and then followed with the clock. Then only we can assign. So here the interface name, interface INTF use. This is the instance name of interface. So what if you want to use, if you want to develop any RTL code, or if you want to develop, if you want to assign any value. So here they are using always block, whether it passes okay, and INTFC. This instance name we have to call, then follow dot, and then we have to follow clock. Then only the interface, then only the signal which is interface, which is inside the interface. Clock is inside the interface. So how to assign the value means like this only. So how to fetch the variables inside interface? We have to use the pointer, right? So we have to use dot operator. Then after followed by the signal. So how if you want to assign any value? So inside interface data also there. So INTF dot data we are assigning some 0 0. So like this is a simple TB. So like this we can assign the values in the TB if you are using anything in the TB. So like this, try to implement T flip-flop RTL code using interface. And anything you can, JK flip-flop we can implement any other memories, we can implement any shift registers, we can implement counters, anything which we want to use, reuse again. Every signal will be declared inside interface. Then that interface will be connected to your RTL. Then we can assign values and we can implement our own logic. How we can implement the logic in the RTL, that can be implemented following using this instance names. This instance name is added before the signal. That's it. So mod ports. So what's the thing? So why we are using mod ports inside interface? So interface inside we are using mod ports. Mod ports are actually a subset of RTL. Let's take there is an RTL. So RTL, let's take if you want to develop multiple RTL codes, or else we have thousands of signals. So with the thousands of signals, we are including them in interface. Okay, interface we are including. So with the thousands of signals, I want to develop different RTL codes or different test bench codes. Now we have to create a subset, right? Let's take in this thousands of signals. So just I have to use 5 signals in this RTL. Now I will declare a separate mod port for this. Actually, subset of interface. Mod port is actually a subset of interface. Then that separate 5 signals can be used in a separate design to implement separate RTL code. And let's take this design actually wants 20 signals from that interface. Now I will create a separate mod port for that, and I use the mod port name to develop the RTL code. Like that, we have to use mod port as the subsets of interface. See how to improve the mod ports. So interface we are declaring. So there, let's take, there are signals, clock, data type. So this is the data. Like this, we can have multiple signals here. So mod port master. So mod port is the input construct, and I am using some master is the instance. Here I am making, so input clock, output data. So for this master, let's take master is a separate RTL. So for this, inputs are clock and output is data. Okay, output is data for this RTL code. Whereas there is separate RTL code again, mod port slave. Input is clock and again input is data. So the signal direction can be decided in the mod ports. So mod ports are actually subsets of interfaces, and you can decide the signal direction also in the mod ports. Like that, interface can be have some small concept like mod port, and also clocking blocks will be there. So this is the clocking blocks. The clocking blocks, why we are using clocking actually? So if you are working in a Verilog, so some synchronization problems will come, some timing mismatches will come. To avoid that one, clocking blocks are uses. Race conditions will come between TB and DUT, and defines input output timing. So timing related things. So that and all will be overcome using clocking blocks. So this is the declaration of clocking blocks. So clocking CB at the rate the passage or negate you can use, and input data output wise. So this is the thing. Like this, this will be included inside the interface. So best coding practices. So prefer logic instead of reg. Instead of reg and why, just prefer logic. Why? Because it can avoid the confusion. Use interfaces for large connectivity. So if you are working with multiple signals or more signals, just use interface. Use meaningful variable names, not just ABC. Just give a meaningful variable names. Separate RTL and test bench code. So try to write RTL in one file and try to write test bench in another file. We will link them separately. We will link them after using just commands. So these are the interface like interview questions. So what's the difference between bit and logic? And some small packet and packet differences they may ask, dynamic versus assertive arrays, and what are the problems you face while developing interfaces, how to solve them, and how many clocks. So can we work on multiple clocks in interface? In single interface we can have multiple clocks, like that questions may be occur. And what's the purpose of using clocking blocks, that you can go through and see. This is actually exercise for you. Write packet arrays, dynamic array examples, simple interface. So connect interface your DUT, how you connect the interface to the DUT, that and all, just work on them. So just to summarize that now, system Verilog actually what it actually extension of Verilog. So all the constructs whatever in the Verilog that will be there in the system Verilog, and rich data types simplify RTL design. So there are so many data types as we learned before now. These are now the simple data types. In few further classes we are going to learn the complex data types like classes, enum data types, struct data types. There are so many other concepts we are going to learn. So arrays actually provide powerful data structures. They will provide powerful data structures. So you can have data manipulation, memory management will be taken place using these all arrays and all. So that will help the verification easily. So since let's take want to verify my complex RTL design. So for that we will need a separate thousands of values. First that value will be stored in an array. From that again will be fetched and that will be given to the inputs for the RTL. Like that verification happens. Interface modifies. So interface actually what? Simplify communication between modules. It actually simplifies the communication. It actually connects the signals. The confusion will be as you have just have a revision. Let's take actually why we are using interface before, to avoid multiple module connections. Verbose connections are there in each module connection that can be easily simplified. And second thing is like the readability increases. You can read the code easily Instead of 100 lines of code, in just 2 3 lines we can give the connection, and by this actually the reusability increases again. Further, we are using interfaces to try to improve them. That's it, students, for this today's class. So the thing is like after completion of us this like class, try to work on the assignments. I updated assignments here with the name of system verilog assignment 1. I updated with this name. Just go through the assignment and just go through the video once again and try to practice as much as you can using whatever the PDFs. We will also provide the PDF and try to learn from ChatGPT, and as much as snippets you practice you can understand. Mostly in the next class I will just introduce the tools what we are going to work, so which tool we can use to run all the simulations and all. In the next class we will decide where. Meanwhile, just go through the data types, basic concepts and all. That's it, guys. If you have any doubts you can let me know. Yeah, thanks for joining, guys. The recorded session will be given in your LMS. Just go through once again. Yeah, thanks for joining.